is explained in the theory. We will see the circuit connection now. So I am going to use SCR. So this is faced like this: KAG, cathode, anode, and gate. So I am just placing it here: cathode, anode, and gate. Is it okay? Then you can see the circuit diagram there. So initially we are going to use this 100 ohms, which is rated with 20 watts. Okay, so I am going to use this resistive load. Okay, so I am going to connect it to anode knob. So middle one is anode knob. I am just using this anode connection, and one more I am just keeping it here. Okay, so one side I have just kept it empty, and one more side I have just connected it to anode. Then I will just connect this diode now. So diode, positive terminal and negative terminal. So negative terminal is connected to gate, okay, and positive terminal, that is P type is connected to some point, okay, where I will be taking R and C values which are variable. So I am going to use decade resistance box and decade capacitance box. So decade resistance box is here. So positive, you can just see there. So before connecting this, I need to use some 100 ohms. So I will be just using this 100 ohms resistance for safety purpose. So which is again connected to anode. One terminal is connected to anode, and one more terminal is connected to some point. Okay, so I am just connecting it here. Then, so you can see in the circuit diagram. So the other terminal is connected with some more resistance, that is one terminal of DRB, that is a decade resistance box I am connecting, and this negative I am going to connect it to a P type Zener diode. So not Zener diode, normal diode. Okay, I am repeating. DRB positive terminal is connected to one terminal of this 100 ohms, then negative DRB terminal is connected to a P type of diode. Is it okay? Similarly, you can see in the circuit diagram we have to connect as DCB also, that is a decade capacitance box. So I am just connecting this positive decade capacitance box to one point, that is near P type of this diode, and negative I will be just using it for minus 12 grounding purpose. Okay, so I will be using this ground point somewhere here. Okay, so I will be using somewhere here. Done. Then you can see here I am left out with cathode connection. So I will be just using this KAG, right. So cathode I am going to ground it directly. Instead of telling ground, I will be connecting it to minus 12. Done. And one more, that is one more terminal that is left out is only supply, that is plus 12 and minus 12. So plus 12 I will be connecting it to one point, that is power resistor, and one more minus 12 as usual I just said now. So I should use it as a ground point. So plus 12 to minus 12, totally I am using 24 volt peak to peak. So this is all about the connection. To see the output, okay, so you can see I am going to use two CROs, two DSOs. Okay, so first DSO I am going to connect it to across this load, and one more across this anode to cathode. So I need two outputs. So what I will be doing is one across this SCR. Okay, I am repeating. I will be using this for seeing the SCR output. So one is across this anode and cathode. Okay, so you just connect across this anode and cathode. So I am just connecting anode to cathode, or you can just take it reverse if you want. Okay, and you can just invert the output. Okay, so one output I am going to keep it at cathode to anode, and one more across this load. So I am just placing this across the load. Okay, so positive I am just connecting it to here, and the negative I am going to connect it to anode terminal. So this is all about the connection. Then what you can do is you can just turn on this, and you will be getting the output. So initially I will be keeping this resistance like this, and we will start the experiment. So now you are able to see two different waveforms now. So one is across a load, and one more is across this CR. So I already told you while connecting the circuit. Okay, now so we will just observe this rectified output here. Okay, so this rectified output you can see here. So you are getting some V average component and other things. So now what I will be doing is so for first, without giving any resistance, you are able to see some triggered output here, right. So this is just because we have used some safety resistance around 100 ohms. That is why you are getting around some 0.1 and 2. Okay, 2 deflections. So I already told you. You can see the complete sine wave which consumes 4 boxes. So each box will be 90 degrees. Because the 4 into 9 is a 360 degree, one complete sine wave time period is a 360 degree. So 4 boxes means you will be having only 90 degree in each box. So in each box you can see 5 different scale divisions. So each division I can tell you like this, since it is 2 divisions for only 100 ohms, that is used as a safety resistance, you are getting around 2 boxes. So 2 into 90 divided by 5, because 2 by 5 boxes into 90 degree, that is the actual degree. So if I calculate here, you can see the table. So 2 by 5 into 90 will be equal to 36 degree. So that is how you will be getting alpha value. So for this alpha is equal to 36 degrees. Okay, how much practical voltage you are getting? You can just see there. So practically I am getting around, you can see that V mean, which is nothing but V average, you are getting around 6 volts. So make a note of it. So if you calculate theoretically also, we will see how to calculate that theoretical part. You can see here, you see in the tabular column, you can use that formula, that is VDC theoretical value is Vm by 2 pi into 1 plus cos alpha. What is the alpha value? So alpha value whatever we got is 36 degree, but what is that Vm value? Vm you can just take peak to peak itself, because it is a half wave rectifier output. So you can take peak to peak, it is around 28 volts. So you can take 28. So if you calculate 28 by 2 pi into 1 plus cos 36, it comes around 7.77 volts. So that is what I have put in the truth table, or you can just take it as a tabular column. Okay, so in the tabular column you can see alpha value whatever we got is 2 deflections divided by 5 into 90 degree, because each box is 90 degree. Then you can see VDC practical whatever you have got is 6 volts, but VDC theoretical whatever you are getting by using that formula Vm by 2 pi into 1 plus cos alpha is around 7.77, which is manageable. Then we will go for next readings. So I will just use this 1K knob and I will just increase the resistance to one more 1 kilo ohms. So initially we had 100 and we are giving 1 kilo ohm. So total is it is 1.1 kilo ohm. So in the tabular column for next slot of readings, you are able to see for 1.1K. So now you can see the number of deflections here. So here 1, 2, 3, 4, 5. So 5 box means it is 90 degree, because 5 by 5 into 90. So alpha whatever you got is 5 by 5 into 90, which is nothing but 90 degrees. So for this alpha 90 degrees, how much average voltage or VDC voltage you are getting practically means, you can see there it is around 3.2 volts, right? So for this 3.2 volts practically you are getting. Now we will verify the same thing using theoretical concept. So you can see here theoretically we can calculate using Vm by 2 pi into 1 plus cos alpha. Alpha value we know that it is around 90 degrees, because 5 deflections you got it, right? So now you can see here you are getting around 24.8 as VPP. So same thing you can take it as Vm. So substitute there. So 24.8 divided by 2 pi into 1 plus cos alpha. Alpha value is 90. Substitute. So practically you got around how much? 3.2, and theoretically if you calculate you are getting around 3.94, which is acceptable. So we'll go for next reading. I will increase to 2 more kilo ohms. That is instead of 1.1 I will go for 3.1. So I am just using this knob for 2 times. So it is under 3 kilo ohms. Initially we had 100 ohms. So totally it is 3.1 kilo ohms. For this 3.1 kilo ohms, you can see here number of deflections is around. You can just see here how many deflections are there. So I think 1, 2, 3, 4, 5, 6, 7. So 7 by 5 into 90 degree. So it is 7 by 5 into 90 degrees. So each box is 5 scaled into 90 degree, but it is having a 7 scale. So 7 into 90 by 5. So it is around, if you calculate, you will get around 126 degrees. So that is alpha. So I got alpha value now. Then you can just see there you are getting around V mean as 1.2 volts. I am repeating, you are getting 1.2 volts as mean volts. So you can just make a note of it. So that is what I am getting VDC voltage practically, but I should verify it theoretically, for which I require VM value. So you can take VM as VPP. So you can just see here it is around 18.8, right? So 18.8 you can just take, and 18.8 divided by 2 pi into 1 plus cos alpha value is 126 degree. If you calculate again, you are getting 1.23 volts, which are absolutely matching. Theoretical and practical voltages are matching. And we will go for one more reading. We will increase the resistance to 2 kilo ohms. So it is 3.1 initially, and I will go for 4.1 and 5.1. So I have increased it to 5.1 now. Okay, 5 kilo ohms there and 100 ohms in series. For safety purpose we used that. So total it is 5.1 kilo ohms. For this you can see the number of deflections. So it is around 8 deflections. So what is the alpha value? So you can just fill the tabular column. Alpha value is 8 by 5 into 90 degrees, which is around how much? 144 degree. Is it okay? So for this 144 degree, you just calculate the theoretical value and practical value. Practically how much I am getting? You can just see here 400 millivolts, which is nothing but 0.4 volts. So that is 0.4 volt. So that is how you got a practical value. How to calculate the theoretical value? So for theoretical value, you can use a Vm by pi, Vm by 2 pi. So what is that Vm value? You can see VPP, which is around 12.4. So 12.4 divided by 2 pi into 1 plus cos alpha, where alpha value is 144 degree. If you calculate again, it comes around 0.37 volts. So that is absolutely matching. So these 4 readings are sufficient. If you want, you can go for one more reading. It is left to you. So this is how you are supposed to do this particular experiment. So just take alpha reading. For calculating alpha reading, you can make use of this by varying this resistance value. For safety purpose, we have used 100 ohms, as I already said. Then you can go for increase in resistance, 1 kilo ohm, then 3.1 kilo ohm, then 5.1 kilo ohm, and so on. Okay. For all the readings, whatever I have tabulated, you can just go for next process. So that is all about the experiment. So this is a half wave rectification using RC triggering. Okay. So that is all about the experiment. Next we will see full wave rectification using RC triggering. So now I am going to tell you the connections. So you know this 4 diode method for full wave, right? So I have connected 4 diodes. So where I can give the supply, okay, and this part is grounded. Okay, I am using this as ground, and you can see power resistor is connected here, which is directly connected to anode terminal of SCR. Is it okay? Then I have used this diode, okay, that is required for giving RC triggering. So I will just connect this DRB and DCB now. So DCB, before that I will connect a DRB. Okay, so positive terminal of this DRB is connected to safety resistance 100 ohms. I have connected this 100 ohms. Instead of directly connecting this DRB to anode, I am using safety resistance 100 ohms followed by this DRB. So positive I will be connecting there, and the negative I am just connecting it to P type of diode. Okay. Similarly, you can just see here, so this capacitance also we should connect in the same fashion. So I am just connecting this DCB, okay, here, okay. Then I am just connecting this DCB positive terminal to P type. Is it okay? Then this negative terminal of this capacitance, okay, be careful, you should ground it, okay. You should ground it. So everything is done. Now we will go for power supply, that is plus 12 and minus 12. Okay. So in order to connect plus 12 and minus 12, I will be using across this diodes. Okay. So plus 12 I am connecting at one point, minus 12 I am connecting at one more point. Is it okay? So the connections are done. Then it is our duty to see the waveforms, for which we require probes. Okay, CRO probes. So now I will be using this across this anode to cathode. I already told you, better you connect it as cathode to anode because of reference points. Okay. Okay. Cathode to anode. This is across SCR. Then this will measure voltage across SCR. Then this. Okay. One more DSO I am using for measuring voltage across load. So positive, I will connect it across this power resistor. I should measure the output voltage, one at this point and one more at anode point. Is it okay? Anode point. So now everything is ready. Okay, we will go for seeing the expected output. Before that, we will just switch on this power supply. Okay, and now you can see the expected output. You are getting the full wave rectified output, which is not controlled. But what we will do is we will control this using RC triggering. Okay. So for example, I will just vary this DRB, and you will be getting the expected output. So we will see the tabulation reading. Before that, I will make it 0 and we will start the experiment. Okay. So now already I shown the circuit associated with full wave rectification using RC triggering. So now I am going to tell you how to tabulate the readings. First and foremost, as we did in the half wave rectification using RC triggering, we had to tabulate alpha value followed by what is the output VDC voltage theoretically as well as practically you have to calculate. So in the tabular column I am going to show now, you have to tabulate. First and foremost, I will go for increase in terms of 10 kilo ohms because it is full wave. So initially without giving any resistance, you can see there is some minute deflection, that is just because we have given some 100 ohms safety resistance. Now I will go increase this resistance value to 10 kilo ohms. So 10 kilo ohms, that had 100 ohms, it is negligible. So for 10 kilo ohms, you are able to see some readings now. So alpha, how to calculate alpha? You can see this voltage output, which is across SCR, and that is across the load. Okay. So if you see this voltage across this SCR, you can see so many deflections. So now you can see 1, 2, 3, 4, 5. Actually 5 deflections, but it is each deflection is 9 degrees because 4 boxes will cover the entire sine wave. So 4 boxes means in each box you have 5 deflections, so 20 box. So 20, whenever I say 20 different points, it is 4 plus 4, totally 8. So 8 5s are 40, 40 means 40 points are there. 360 degree by 40 means each division is 9 degrees. So you can see number of deflections here. So 1, 2, 3, 4, 5. So there are 5 deflections for which you can see the calculations now. There are 5 deflections divided by 10 because it is for calculation of alpha. So 5 by 10 into 90, it will be 45 degrees. Is it okay? So I am repeating, there are 5 deflections. So each deflection is 9 degrees because 90 by 10 is 9 degree. So 5 into 9 is 45 degree. So for this 45 degree, whatever the value you can see here, that is a VDC, it is around 10.8. You can see that. Okay. So VDC is around 10.8. So similarly, you can calculate a theoretical VDC value also. For that, you can use the formula Vm by pi into 1 plus cos alpha. It is Vm by pi. Instead of 2 pi, we will replace it with only pi because it is full wave. Okay. So for that we require cos alpha means alpha value. So alpha value I already calculated, it is around 45 degrees. For this alpha 45 degree, you can put that in 1 plus cos alpha. But what is that Vm? Vm, you can see there is some VPP value, which is a deflection around 21.2 to 22. So I will take it as 21.2. So you just go for practical calculations as shown in the tabular column. So it is 21.2 divided by pi into 1 plus cos alpha, where alpha value is 45 degree. So now you can see the calculations. Theoretically it is around 11.5 volts. Is it okay? So we will go for next reading. I will increase the resistance by 10 more kilo ohms. So for this 20 kilo ohms, you can see the deflections now. So there are around 1, 2, 3, 4, 5, 6, 7 deflections you can see. 7 into 9 degrees, or you can say it as 7 into 90 by 10, which is around 63 degrees. Okay. So for this alpha is equal to 63 degree, you can see the VDC practical voltage is around 8.8 volts. So 8.8 volts I am getting practically. And how to calculate theoretical VDC? So for that we require Vm by pi. What is that Vm? So you can ask VPP. So VPP, it is around 21.2 again. So use the 21.2 divided by pi into 1 plus cos alpha, where alpha value is 63 degree. So if you calculate theoretically, you are getting around 9.8 volts, but theoretically you got 9.8, but practically it is 8.8. Okay, acceptable. So now we will go for one more reading. I will increase this resistance by 10 more kilo ohms. So it is totally now 30 kilo ohms. Okay, for this 30 kilo ohms, you can see exactly there are 10 deflections, which is nothing but 90 degree alpha. So 10 into 90 by 10, which is nothing but 90 degrees. So alpha value is 90 degree, for which you are getting 6.4 volts VDC practically. So how to calculate theoretically? So use the same Vm by pi into 1 plus cos alpha. So where Vm is around 21.2 again. So 21.2 divided by pi into 1 plus cos 90, it comes around, you can just calculate. So it is around 6.74 volts, and theoretically you got 6.7, but practically you are getting 6.4, which is almost matching. Then we will go for one more value. I will go for 40 kilo ohms. Okay. So for 40 kilo ohms, you can just see how many deflections. So you can see here around 12 deflections are there. So 12 into 90 by 10, which is around 108 degrees, 108 degrees. So alpha is 108. Then you can see what is the VDC practical output. It is 4 volts. So you can see here. So you are getting around 4 volts. So you just tabulate there. Then you can just see VPP, that is around 20.4. Okay. So 20.4 divided by pi into 1 plus cos alpha, where alpha is 108 degrees. So if you calculate this, you are getting 4.48 volts. So practically you got 4 volts. Theoretically you are getting 4.4. Okay. So it is also acceptable. So this is how you are supposed to do the experiment. So if I go for 50 kilo ohms, entire thing it vanishes. So better you stop at that stage. If you are willing, you can try for 41, 42, 43 kilo ohms also. So this is all about tabulation of the readings. So that is all about SCR triggering using RC method. Okay, RC triggering for a full wave and half wave rectification using SCR. Thank you.